We continue our discussion with laws of motion. We have already discussed Newton's second law of motion as well as Newton's first law of motion. So let us look forward at Newton's second law of motion again. So from the mathematical expression of Newton's second law was something like this: F is rate of change of momentum. The force applied is equal to the rate of change of momentum. From here you can easily write change in momentum is equal to the product of the force and the time interval during which the momentum change is occurring. So you can say that to produce a given change in momentum, we can apply a force for a definite time interval. If the force is sufficiently large, then the time interval might be very small. That means a given change of momentum can be brought about by applying a large force for a small duration. A change in momentum can be produced by a large force acting for a short duration. So this might be a realization of this mathematical expression. For example, a required momentum that is imparted to a body by applying a force of large magnitude for a short duration. We have several examples of this. For example, if we apply a very large force, that is frequently done when a batsman hits a cricket ball with his bat. So when the batsman is hitting the ball with the bat, the force applied by the bat is very large, but the duration of impact is very small, and that produces a large change in momentum of the cricket ball. Similar situations are also observed while we are hitting a tennis ball with the help of a racket, or we are hammering a nail into a wall. So in these situations, the force applied is very large, but the duration of the impact is very small, as a result of which a large change in momentum is obtained. So let us again take the example of the cricket ball being hit for a short duration, or say for example, in a cricket field, while catching a ball, a cricketer usually withdraws his hand, and in this situation, that large change of momentum is produced by a force acting for a large duration of time. Remember that while hitting a cricket ball, the force exerted by the cricket bat is large, and the force acts for a very short duration. That produces a large change in momentum. But while catching a cricket ball, the fielder increases the time of impact of the force in order to reduce the impact on his hand. So both the situations occur. Either the force is very large, acting for a very short duration of time, or in order to decrease the impact of the force, the time interval of impact might be increased, so that the change of momentum is easily negotiated by applying a force acting for a very large duration. So for example, while catching a ball, a fielder withdraws his hand. Now, from a mathematical viewpoint, you can say that suppose the initial velocity of the ball is u and the mass of the ball is m. Initial velocity of the cricket ball and mass of the cricket ball is, suppose, small m. Obviously, the initial momentum is mass into velocity, that is mu. Now, when the cricketer stops the ball and he ultimately catches the ball, that means when the ball gathers in his hand, definitely the final velocity of the ball is 0. When the fielder catches the ball, velocity of ball is, suppose, small v, which is 0. That is the final velocity of the ball is 0. So final momentum is obviously is mv, that is m into 0, which is obviously 0. So the final momentum is 0. So therefore you can find the change in momentum. So the change in momentum is obviously the final momentum minus the initial momentum, and the change in momentum is delta p equal to 0 minus mu, which is minus mu. In terms of the value, the momentum, the change in momentum is mu, but the negative sign indicates that the momentum change has occurred opposite to the direction of the motion of the ball. That is, your change in momentum is in direction opposite to the initial direction of momentum. So numerically, if you are interested in the value only, you can say delta p is mu. Negative sign has nothing to do with the magnitude of the value. The negative sign indicates opposite direction. So change in momentum is mu. Now, if the cricketer does not pull his hands backward, the fielder, suppose, is withdrawing his hand, what I have said, but suppose the fielder has not withdrawn his hand. So the force applied is F1, which is change in momentum by time. Now this time of impact is very small because the fielder has immediately stopped the ball. So here T1 is very small. Now in the next situation, suppose I assume that the fielder has withdrawn his hand in the backward direction. If the fielder pulls his hands back, and stops the ball, he now allows the time of impact to be large as compared to the previous case. Because the fielder has pulled his hands back and he has not stopped the ball immediately on impact, that means he has used a longer time to stop the ball. The force applied is, suppose, F2, which is again change in momentum by a time t2, and as I have said, the time t2 is large. So now if you compare F1 and F2, you definitely can observe that which of the force is greater. So since your T2 is greater than T1, obviously F1 will be less than F2. Sorry, F2 will be less than F1. Since T2 is greater than T1, so F2 will be less than F1, because you see that F1 is inversely proportional to T1 and F2 is inversely proportional to T2. So more time means less force. So in this case T2 is greater, so F2 is less, T1 is smaller. Sorry, T2 is greater, so F2 is less, T1 is smaller, so F1 is greater. So obviously in the second situation the force applied is small. So we can say that the cricketer or the fielder can avoid any chance of injury by withdrawing his hands along with the moving ball while catching it. So this is an important result that we can realize from Newton's second law of motion. As the force exerted on the hand, so this is the force exerted on the hand by the ball, F2, is small as compared to the force exerted by the ball on the hand when the time of impact was small. So now this force is definitely small. It means the ball has taken large time to exert the force, and this saves the fielder from getting any injury. So definitely if you can increase the time of impact in certain situations, you can reduce the force considerably. So some other examples also you can take. Say for example, athletes often land on sand or foam after taking a high jump. So when an athlete is actually landing from a height in a pole vault or in a high jump, he or she might hurt his or her feet if they come to rest almost suddenly, if they hit the hard floor directly. So that's why, in order to avoid getting injured, definitely when the athlete actually lands, sand or foam is laid on the floor or on the field, so that the time of impact of the force is increased. And if the time of impact of the force is increased, as we have demonstrated here, if the time of impact of the force is increased, then the athlete will get a very less injury. Actually, they don't get any injury because of the sand or foam that is spreaded on the surface. So the force exerted is being reduced by increasing the time of impact, and they are saved from getting injured. So you can also see such examples in daily life. For example, glass vessels, if they fall on a hard floor, they will definitely break, because when they fall on the hard floor, the time of impact is so small that a considerable large force is exerted by the ground on the glass vessel, and it automatically breaks. But if the glass vessel is made to fall on some carpet or sand, then the time duration in which the vessel comes to rest on the carpet or on the sand is definitely large. And as the time duration is large, so the force exerted by the floor over which carpet or sand has been laid is reduced, and therefore they do not break. So there are so many examples that you can realize, and they can be analyzed mathematically as well as from theoretical viewpoint to demonstrate Newton's second law of motion. So now let us solve two problems related to Newton's second law of motion. So the first problem is like this. A bullet of mass 50 gram is moving with the initial velocity of 100 meter per second. So let me assume that the mass of the bullet is m, mass is 50 gram, which means 50 by 1000 kg, which is obviously 5 by 100, that means that is 0.05 kg. The initial velocity we generally denote by u. The initial velocity is 100 meter per second. It strikes a wooden block and comes to rest. Means the final velocity is obviously 0. Because it comes to rest, the final velocity v is 0. And in that process it penetrates a distance of 2 cm. So let the distance be denoted as s, that is 2 cm, which means 2 by 100 meter, which can be written as 0.02 meter. Now you have to calculate the initial momentum of the bullet. So the initial momentum, let me call it as P1, momentum we denoted by P. So the initial momentum let me call it as Pi, suppose initial momentum, which is equal to mass into initial velocity, that is mu, that is 0.05 into 100, which means it is 5. What will be the unit? The unit of momentum is kg meter per second, because mass is kg and velocity is meter per second. So the unit is kg meter per second. So we have got the final momentum. Now you have to calculate, this is the initial momentum. You have to calculate the final momentum. Obviously the final momentum is 0 because the body has come to rest. So the final momentum Pf is mass into final velocity, which is obviously 0.05 into velocity was 0, final velocity, so that is 0 kg meter per second. Now we have to calculate the retardation produced by the wooden block, and then you have to calculate the resistive force exerted by the wooden block. Now in this problem you can see that initial velocity, final velocity and distance covered is given. So you can use the formula v square minus u square is 2as, and then you can find the retardation. V square minus u square is 2as. So here v is 0, so that is 0 square. What is u? U is 100 meter per second, so that is 100 square. 2 into a into what is s? S is 0.02. So from this obviously you get 0 square is obviously 0, minus 100 square is 10,000, and from here 2 into 0.02, you will obviously divide here, that is 0.04 will be the acceleration, a equal to minus. So now 0.04, if 2 places of decimal are shifted in the denominator, it means that you are multiplying 100 in the numerator. So now you can simplify this as from this statement. I can omit the previous calculations. You can note it down. Okay, let me omit this section. I have already calculated initial and final momentum. So from here on, you can get a equal to minus 10,000 by 0.04, which means 100 into 10,000 by 4. 100 by 4 is 25. 25 into 10,000, which can be written as 10 to the power 4 zeros. 25 into 10 to the power 4. Obviously the negative sign is there, or you can write minus 2.5 into 10 to the power 4. So the acceleration is negative. It means this is retardation. Hence you can say that retardation, as the question has been asked, what is the retardation? So whenever you are writing the value of retardation, you will not use the minus sign, you will just write the value as 25, 2.5 into 10 to the power 5, sorry, 10 to the power 5 meter per second square. If the question was what is the acceleration, then your answer will be acceleration is minus 2.5 into 10 to the power 5. But the question is retardation, so you will write the positive value, that is 2.5 into 10 to the power 5. And the final is the resistive force. So the fourth part of the question is the resistive force. This is the third part and this is the fourth part. Obviously F equal to ma. Now here the question is what is the resistive force. So we will apply the positive value, that is the value of the retardation, because the question is the resistive force. So mass was, if you remember, it was 50 gram, so 50 by 1000, that is 5 by 100, that is 0.05, into the positive value, that is 2.5 into 10 to the power 5. So you can shift 2 zeros here. So here, from here you can omit 2 zeros. So you can write this as 2.5 into 10 to the power 3, which means 5 into 2.5 is 125, or 12.5 into 10 to the power 3, which gives you 125,000. You do point, you will get 1 0 less. So this is 12500 Newton. 12,500 Newton is the answer. Similarly, or we say that on a similar basis, we can continue with the next problem. The next problem is, it is given that a car is moving with a uniform velocity of 30 meters per second. It is stopped in 2 seconds by applying a force of 1500 Newton. By applying brakes, you have to calculate the change in momentum, the retardation and the mass of the car. So uniform velocity of 30 meters per second, that is the initial velocity u, is 30 meters per second. And obviously because it has been stopped by applying brakes, so the final velocity is 0. So the change in momentum delta p is equal to your final momentum minus initial momentum. So final momentum will be m into 0. But in this case, if you observe, you don't have the value of m. So you can keep it in this manner. Instead, what we can do is, we know that the force is equal to rate of change of momentum. So change in momentum is equal to force into time of impact. So if you observe the question minutely, the force is given and time of impact 2 seconds is given. So this is obviously, force is 1500 and the time of impact is 2, which means that the change in momentum is 3000. Obviously 1500 into 2, which means the change in momentum is 3000 kg meter per second. Now to calculate the retardation produced. Again you can calculate it from the value of F equal to delta P by delta T, but the mass is not provided. So what you can do, you can again use the formula V square minus U square is 2as. So V, that is the final velocity, is 0. U, initial velocity, is given as 30. In this question it is 30. So the car was moving with a uniform velocity of 30 meters per second into A. The distance travelled is again not known. So what we can do here, we can apply V equal to U plus AP. So this equation we have to know the value of the distance covered. Because distance is not given, there is no need to use this formula. You can use V equal to U plus AP. So final velocity is 0, initial velocity is 30, time is 2. So you get minus 30 as 2a. So a is equal to minus 15. 30 by 2 is obviously 15. So If the question is what is the acceleration, then your answer will be minus 15 meter per second square. But the question is retardation, so you will write the positive value. So therefore your retardation is 15 meter per second square. Now you can calculate the mass of the car. The mass of the car can be determined from this equation itself. If you remember, change in momentum is mass into change of velocity, and we already know what the force is. From that you can calculate mass, either from this one or from the equation F equal to ma. So let me use F equal to ma, which will be much simplified. So the retarding force was 1500, and the retardation that we will use is 15. So obviously you can say 1500 by 15 is 100. So m is equal to 100 kg. This equation could have been used, but change in momentum value you can take. I can show you alternatively what you can do. Now from this one, change in momentum is mass into change of velocity. So change in momentum already we have used and determined 3000 kg per second. Now in this case there might be a problem with the positive and the negative sign, but because the force is applied to the brakes, that means the vehicle is stopping, which means the braking force is opposite to the direction of the motion of the car, and so the change in momentum should be negative. So the change in momentum should be taken as minus 3000. The change in momentum is negative, means its numerical value is 1000, but it is negative means the braking force is being applied opposite to the direction of motion of the car, and so the change in momentum is oppositely directed, opposite to the initial direction of motion. So from here m, what is the final velocity? 0, and the initial velocity was already 30. So from here you get minus 3000 is equal to, obviously 0 minus 30 is minus 30 m. So your negative signs cancel out. 3000 by 30 is obviously 100. So this is an alternative way through which you could have calculated the mass of the car. We come across several forces in nature which are either contact force or non-contact force. Now contact forces are forces which act between different bodies when they are in actual contact or when they are in physical contact. And non-contact forces are obviously those type of forces which act between different bodies when there is no visible contact between them or they are separated by some distance. So many examples of contact and non-contact forces can be taken. So for contact force, let us take the example of the frictional force that acts between a body and a surface. Suppose a vehicle is moving on a road, the force of friction acts between the tire and the road, and the force of friction tries to retard the motion of the vehicle on the road. So this type of frictional force is definitely an opposing force. It opposes the relative motion, you can say, between two objects. The frictional force opposes the relative motion between two surfaces or two objects, a body and a rough surface. Many such examples you can take. The force of friction acts between obviously two solid surfaces, but in liquids also or in gaseous medium also there is a type of friction which we don't usually call friction, but that is almost similar to that of frictional force, and that force is called as viscous force or the force of viscosity, viscous force or viscous drag. So that is also a type of internal frictional force that acts in liquids whenever there is a relative motion between the layers of the liquid. So like friction, the force of viscosity or the viscous drag or viscous force, whatever you may call it, acts between the layers of the liquid and it tries to oppose the relative motion between different liquid layers. So it is also a type of contact force. The reaction force or the normal reaction force is also a type of contact force. So suppose you keep an object on the floor. So suppose this is the body having a definite mass and a definite weight is kept on the floor. Then the floor will exert a force in the vertically upward direction, which is called as the normal reaction force, and that normal reaction is counterbalanced by the weight of the body acting vertically downwards. So definitely the normal reaction force is a contact force. Actually, this normal reaction and the weight counterbalancing each other is a force which is action-reaction pair, and that we will come across in Newton's third law of motion. So this is a reaction force with respect to the weight of the body acting vertically downwards. So the weight of the body is acting vertically downwards. If you call that weight as the action, then the reaction force exerted by the floor on the body in the vertically upwards direction is the normal reaction. The force of tension, whenever we stretch a string, the force of tension that will develop whenever we stretch a string is called as the, you can call it as a contact force. Say for example, a string is suspended from a rigid support and you apply a force in the downward direction. You try to stretch the string, suppose you call this force the effort, then automatically a tension will develop in the string which will act in the vertically upward direction, and definitely that is a contact force, because you need to have a physical contact with the string in order to pull it, and the tension will develop in the vertically upward direction. It always develops in the direction of the support. So because the string has been supported from this point, the tension is acting towards the direction of support. So friction, viscous force, normal reaction, tension are all contact forces. Whenever a body collides with another body, that is also a contact force. For example, suppose two bodies are moving along two different directions. Suppose the body A is moving in this direction and the body B is moving in this direction, and they eventually collide. So at the moment they collide, they exert a force on each other. One force exerted by the body A on B is along this direction, and the body B exerts a force on A along this direction. So these are forces which are definitely developed when the bodies are in contact during their state of collision. So you can call this force as force exerted by A on B, and this can be called as force exerted by B on A. So these forces are both equal and opposite according to Newton's third law. We will discuss that later, but for the time being, you can say that force acting between two bodies when they are colliding is also a type of contact force. So this is what I have saying, force acting between two bodies when they collide. So there are many such contact forces that we frequently encounter in nature. As far as non-contact forces are concerned, non-contact forces are basically the gravitational pull between two bodies. Non-contact force, the force of gravity. Or the gravitational force. We will discuss this in details afterwards, but for the time being, if there are two bodies of masses m1 and m2, suppose there are two bodies of masses m1 and m2 respectively, and suppose they are separated by a distance r apart, then a force of gravitational pull or gravitational attraction exists between this pair of bodies, and the gravitational pull is proportional to the product of the masses and inversely proportional to the square of the distance. So more is the distance of separation, lesser will be the gravitational attractive force. Remember that it is always attractive in nature. If you say that the body 2 pulls the body 1 along this direction, then definitely body 1 will pull this body 2 along this direction. So this gravitational pull is a non-contact force, and it is proportional to the product of the masses of the bodies and inversely proportional to the square of the distance. A similar type of force which is non-contact is the electrostatic force between a pair of charges. Electrostatic force. So if there are two charged bodies and they are carrying some definite amount of charge, then there is a force of attraction or repulsion between those two charges. Suppose this is a body having a charge q1 and there is another body having a charge q2, and their distance of separation is suppose r. Then the electrostatic force is proportional to the product of the charges and inversely proportional to the square of the distance between them. So again, this is a type of non-contact force because there is no need of any physical contact between the two charged bodies. Now this force can be either repulsive or attractive. If q1 and q2 are like charges, the force will be repulsive. If they are unlike charges, the force will be attractive. A similar force is a force that exists between a pair of magnets, which is called as the magnetic force. And the magnetic force is also similar to that of electrostatic force. If there are two bar magnets, suppose, and their separation is larger, the magnetic force will decrease. More close the bar magnets are, the force will be more prominent. And as far as possible, if you remember that in the case of like charges there is repulsion and unlike charges there is attraction, in the case of magnetic force also, like poles will repel and unlike poles will attract. But magnetic force and electrostatic force and gravitational force, they are all non-contact force, and one thing is common about them is that the force weakens with increase in separation between the bodies. If the distance between the given bodies is large, the force is quite small. So you can say that there is a general characteristics of all these forces, of all the non-contact force. So we can say the magnitude of all non-contact forces that I have discussed so far, the magnitude of all these non-contact forces depend on separation, depend on distance of separation. That means more the distance of separation, lesser will be the force, and less is the distance of separation, more will be the magnitude of the force. And among gravitational, electrostatic and magnetic force, gravitational force is always attractive, whereas electrostatic force might be attractive, might be repulsive. Magnetic force is also either attractive or repulsive. So this is a brief realization of contact and non-contact forces. Units of force. So units of force are either CGS unit or SI unit. In CGS unit, the unit of force is dyne and the SI unit of force is Newton, which is just written as N. Now, you know the relationship force equal to mass into acceleration. So whenever you are using either CGS or SI unit, the unit of force is equal to the unit of mass and the unit of acceleration. Unit of mass in CGS is gram and that of acceleration is gram centimeter per second square. So this gram centimeter per second square is actually called as dyne. And in case of Newton, the unit will be kg meter per second square, because mass is in kg and acceleration is in meter per second square. So this kg meter per second square is called as Newton. So you can definitely have a relationship between Newton and dyne. So 1 Newton is how much dyne? So 1 Newton is 1 kg meter per second square, meter per second square, and 1 kg is obviously 1000 gram, 1 meter is obviously 100 centimeter, and second square remains same in both CGS and SI. So this is 3 zeros and 2 zeros, that is 10 to the power 5 gram centimeter per second square, and gram centimeter per second square is obviously dyne. So you can say that 1 Newton is 10 to the power 5 dyne. On a similar basis, we can define the gravitational units of force. So these are, you can say, the absolute units of force, and gravitational units of force are those in which we consider the force of gravity and analyze the units of force. So say for example, in terms of the force of gravity, so in CGS we have 1 gram force. 1 gram force or 1 GF is 980 dyne. Now what is 1 gram force? So 1 gram force is the force of gravity on 1 gram mass. It is the force of gravity on a body of mass 1 gram. 1 gram. So if there is a body of mass 1 gram, the gravitational pull on that body is 1 gram force. So how we achieve 980 dyne? Now force of gravity is equal to mass into acceleration due to gravity. Now your mass is 1 gram, and g, that is acceleration due to gravity, has the value 980 centimeter per second square in SI unit. Now you see that 1 into 980 is obviously 980, and gram centimeter per second square is nothing but dyne. So what we get is 1 gram force. 1 gram force is 980 dyne. Similarly, if you consider the force of gravity and take the SI unit, then what you have is 1 kgf, and 1 kgf is 9.8 Newton. Now what is 1 kgf? It is the force of gravity on a body of mass 1 kg. So if there is a body of mass 1 kg, the gravitational pull on that body is said to be 1 kgf. Now why 1 kgf is 9.8 Newton? Again we apply the formula F equal to mg. Force of gravity is equal to mass into acceleration due to gravity. So this is 1 kgf, means you are taking 1 kg and the value of g, that is the gravitational acceleration, is 9.8 meter per second square in SI units. So this is what you have, 1 kg, 1 into 9.8 is obviously 9.8. This is kg meter per second square, and kg meter per second square is Newton. So 1 kg force is 9.8 Newton. So then obviously we have this relationship, how much is 1 kgf and 1 gf related. So you see that if you multiply 1 kgf by 1000, you will get this time. So not by 1000 directly you can say, but still if you know the relationship between dyne and Newton, you can do that. So 1 kgf is 9.8 Newton, and we know that 9.8 Newton is 10 to the power 5 dyne. So from here, if I write 98, we will get 10 to the power 4 dyne. So again, if I take 1 0 from here, I get 980 into 10 to the power 3 dyne. 980 dyne, it is 1 gram force. 980 dyne is 1 gram force. So this is what you get is 10 to the power 3 gram force, because 980 dyne is 1 gram force. So ultimately 1 kgf is 1000 gram force. 10 to the power 3 means obviously 1000. So therefore 1 kgf is 1000 gram force.